Okay. Does anybody have any questions about what we did on Friday in terms of hybridization and starting to think about sketching orbitals? I had a number of questions about resonance structures, but I'd like to just kind of finish up the hybridization discussion, and the three compounds that I'd like to finish up with are using sulfur. So the idea of SF2, SF4, and SF6. And the way we would handle these three compounds is exactly the same way we did carbon. So we'll start with sulfur. Sulfur is right below carbon on the periodic table. So we would start then with a 3s orbital and a 3p orbital. And so we would have 1, 2, 3, 4, 5, and 6. Right, would be our, let's see. No, it only has 4 valence electrons, sorry. So when we start with sulfur, no, that's right. Right. So when we look at SF2, because this is sulfur, not carbon, so there's 6 valence electrons. So when you look at sulfur in its ground state then would have 2 lone pairs and 1 unpaired electron each. And so if I'm forming SF2, I don't have to go into any excited states, because all I have to do is say, well, my fluorine has 3 lone pairs along with an unpaired electron. So if I want to form SF2, all I need to do is just add a fluorine to one side and then a fluorine to the other. Share those electrons, so now I have my SF2 molecule, which would be analogous to like H2O in terms of looking at the geometry. So my two questions are, what's the hybridization of the fluorine and what is the hybridization of the sulfur? Okay. So we're not into expanded octets yet. So let's go ahead and choose using the cards that I gave you. And if you're missing and if you didn't bring a card, I have some extras. But let's start with the idea of fluorine. What is the hybridization here of fluorine using the rules that we used last time? Is it sp, sp2, or sp3? Okay. And if you're like, if somebody's blocking you, just hold it up as high as you can. Okay, let's see what we have. Okay, we have 6 SPs. We have 10 SP2s, and we have 13 SP3s. Assuming everybody knows how to use the cards. So what I do The way I handle these situations where we have a split is I give you a minute to discuss with people around you, and then we will re-vote and see after you've had a minute discussion if the vote goes towards one or away from one. So take a minute, discuss, what did you say, why did you say it, and then we'll re-vote. Okay, let's go ahead and re-vote then. If you know, after your discussion, now how are you going to vote? Still A, SP, SP2B, SP3C. Okay. Okay, we move to 27 SP3s and 4 SP2s. So what's the correct answer? It's going to be SP3. So what were our rules? The rules about hybridization is it's going to equal the number of hybrid orbitals. How many hybrid orbitals in the fluorine? The number of lone pairs plus the number of single bonds. So I got 3 lone pairs, a single bond. That means I have 4 hybrid orbitals. How do I get 4 hybrid orbitals? sp3. So the fluorine is going to be sp. Now, let's do the same thing for the sulfur. So what would be the hybridization of the sulfur in SF2? A, SP, B, SP2, 3, SP3. So what would be its hybridization? They're right below. A is SP, B is SP2, and 3 is, or C is SP3. For sulfur in SF2. It doesn't form an expanded octet yet. In the next couple, we'll have an expanded octet, but for this one, we don't. So those are our 3 choices for sulfur. Okay. Okay, what do we have? We have 31 SP3s and 0 everything else. Okay? Right. So the idea here is, I think we got it. Okay? So that's the way you always have to remember. Number of lone pairs plus number of sigma bonds gives you number of hybrid orbitals. Number of hybrid orbitals gives you the hybridization. Okay? So now what about SF4? How am I going to form SF4? And the issue with SF4 is, I'm going to do this, go to the next page. So SF4, we still have our 3s and our 3p's. So we have our 6 valence electrons. But just like I ran into on Friday with 2 unpaired, I need to generate 2 more unpaired in order to be able to form the bond with the 4 fluorines. So now I'm going to have to promote. So my question is, what is the orbital directly above 3p? There is no 2D. So what's directly above the 3p? The 4s. So if we're going across the periodic table, here's a real quick periodic table. It's S's, P's, and then D's. So the next one would be the 4s. A rule of hybridization is that you cannot hybridize orbitals that do not have the same principal quantum number or shell number. So I can't hybridize the 4s and the 3p. Just like when I did carbon, I couldn't hybridize the 1s and the 2 s's and p's. So what's now next after 4s? The 3Ds. So now I have a 3D, I have 5 3D orbitals. So you might say, well, don't you have to promote into the 4s? Remember, it's all about energy. So I'm going to have to pay an energy price right now to promote. But I can only promote and use that energy if I'm going to get it back. How am I going to get it back? Hybridization. So I'm going to go past the 4s and the 3D into the 3D. So I'm going to promote this electron on up into the 3D orbital. Am I allowed to skip? As long as I pay an extra energy price, which I am now going to get back when I hybridize the S, the P, and the Ds. Okay. And if you remember from general chemistry, the D and the S orbitals are pretty close in energy. Sometimes you would skip them in order to form like a D10 configuration or a D5 configuration. So this isn't out of the ordinary. It sometimes happens. So now what I'm going to do is now in my excited state configuration, I now have a pair in the 3s. I've got 3 unpaired in the 3p, and then in the 3d, I'm going to have a single electron. So just like I did last time, I'm going to hybridize the orbitals. So I'm going to hybridize the D, the S, and the P's. So I'm going to get now a D, S, P3, or it can also be called an SP3D. I don't honestly care. So the key thing is I took 5 orbitals. I'm now going to have 5 hybrid orbitals. What's going to be in those orbitals? It's going to depend on the atom. Remember, hybridized orbitals place electrons into the orbitals after the fact. So I've got 5 orbitals. I now go to Vesper theory and say, what geometry do you get when you take 5 orbitals? When you take 5 clouds of electron density? You get trigonal bipyramidal. So any sp3d orbital is going to look like this. It's now going to have 5 hybrid orbitals. And so then the question now becomes, okay, for the sulfur, let's go ahead and put our electrons into those orbitals. So what am I going to have? I'm going to have a pair and then 4 unpaired. So I'm going to have a pair here, 1, 2, 3, 4 unpaired. And that's now going to allow me to do what? Attach the 4 Fs, the 4 fluorines. So now my fluorines are going to come in, and they're going to share their unpaired electron, and now I'm going to get the 4 Fs. Okay. So over here in the orbital picture, I have to remember kind of, well, where does the lone pair go? and this is a level of detail that I'm not going to commit you to. So you could say, where does the lone pair go? Does it go in the up and down positions? Does it go in the trigonal planar? My recollection is that it goes here, but I could be wrong. So it doesn't matter where we put the lone pair. The critical part is, if I'm sketching this picture, my fluorines, I already said, were sp3 hybridized. So the fluorines are going to have their sp3 hybrid orbitals now overlapping the dsp3 hybrid orbitals of the sulfur, because now I can go ahead and erase that X and put a sulfur there. And then in each of the fluorine orbitals, there's going to be a lone pair. And people will ask me, like, does it matter if the dots go inside or outside the orbital? No. They can go either place, depending on how you drew it. Like, I didn't give myself enough space to put the dots on the inside. So this is what an SF4 would look like. The sulfur would be dsp3 hybridized, and the fluorines would still be sp3 hybridized. And so this would be my orbital. That would be my orbital picture.
How come we had to skip the 4s and go up higher to 3D?
Because to hybridize, you can only hybridize orbitals that have the same principal quantum number. So I can't mix 3s and 4s. I can't hybridize those. I can only hybridize 3s. Which leads us then to, why do elements in row 3 or lower, why are they the only ones that can form expanded octets? Because they're the only ones that have the 3D orbital, or the 4D. There is no 2D, or else we could have an expanded octet for carbon and oxygen. But row 3 now has access to the 3Ds. So that's one of those quantum mechanical rules that you just can't break. So you have to hybridize all 3s or all 4s, but you can't mix quantum numbers, principal quantum numbers. And so it may have cost me a little bit of energy to go past the 4s into the 3D, a minimal amount, but then I get that back by hybridizing. Because when I hybridize, I still get these large lobes of electron density to be able to form stronger bonds. Just like we talked about, or just like I said on Friday for carbon. Okay. Right. Okay. Does that make sense? So then if we were doing SF6, I now need 2 more unpaired electrons. So if I went to SF6, I now would say, okay, I have 3s, 3p, my 4s, my 3ds. I would do exactly the same thing. I would say, I'll start with my dsp3 hybridized excited state, and I'm going to go 1 more. So now I'm going to take this pair of electrons, and I'm going to unpair it and promote 1 into the 3D. And now what am I going to end up with? If I eliminate the 4s, just as I'm now I'm going to end up with 2 Ds, 2 unpaired Ds, 3 unpaired Ps, 1 unpaired S. And so now I can go ahead and I can mix all of those orbitals together. So now I'm going to mix 6 orbitals together, and I'm going to end up with 6 hybrid orbitals that have a 2D and an S and 3 Ps. So either D2 sp3 or sp3 D2. And so those orbitals are all going to have the same energy, but now there are 6 of them. In the case of the sulfur in SF6, we have an unpaired electron in each one of those. So now I would go in and add my unpaired electrons. And now I go to Vesper theory and I say, in Vesper theory, what geometry do you get when you have 6 clouds of electron density? You get octahedral. And so any D2sp3 hybridized orbital or hybridized atom is going to look like this. You're going to have X, Y, and Z planes. How many electrons go into each one? It's going to depend on the atom. So in this case, there's 1 unpaired electron in each one of those for the sulfur in SF6. So that kind of completes the story in terms of hybridization. Everybody kind of with me? Okay. So we'll come back here in a couple minutes, and then we can do one of these problems. If I give you a molecule, can you sort of sketch out the orbital picture? Okay. But what I want to do is take some time here for resonance as well. So, were there any questions about the resonance structures? There were some questions about arrows and how arrows basically mean the movement of the electrons, and you're showing the direction of the movement of the electrons, and they always move towards a positive charge if there is a positive charge to move to. Okay. I don't hear any questions.
There's like 3 different types of arrows, right? How do you know like when to use
No, well, actually, there's just 2 arrows.
Okay.
There's just 2 kinds of arrows. There is a half arrow, or what a lot of books call the fish hook arrow. This means that I'm moving only 1 electron, is what that one means. When it has a full head on it, that means I'm moving a pair of electrons. So I'm moving 2. The fish hook arrow we will deal with towards the end of the semester, because we deal with this when we have radicals. A radical being a carbon with an unpaired electron. This is a radical. And radicals are unstable species because they don't have a completed octet. And so what they will do is they will react with other species in order to get an electron, or actually get an atom with an electron to form a bond to give it its octet. So these are radicals. They're sometimes called free radicals. Right? In nutrition, free radicals, you're always taking antioxidants to try and defeat free radicals that are in your system. How do free radicals get in your system? There's lots of ways. One of the necessary ways is that if you remember back to general chemistry, oxygen gas has a diradical form that is paramagnetic. And we know that oxygen has a paramagnetic form because if we have a large magnet and we pour liquid oxygen through it, if you've ever seen that demonstration, or I'm sure it's on YouTube, that the oxygen the liquefied oxygen is attracted to the poles of the magnet, that means it's paramagnetic. So in our system, this can come from just breathing. Right? If you breathe in oxygen, you have these unpaired electrons on the diradical oxygen that can go around and start reacting with different molecules. And of course, your option here is if you don't want the oxygen diradicals, you just don't breathe. Right? So there's no option. We have to take that in. There's other things, there's copper and iron species that can cause these radicals, that can cause these types of radicals to form. And radicals will react and they will pull off hydrogens from other atoms. So we'll talk more about that. They're just introducing. The one thing that this book tries to do, effectively or not, is to introduce stuff that we're going to encounter later on, early on. And what I found is that even if I go over it early on, I'm still going to go over it later on, because there's time in between then and now. So we could go through all the free radical stuff, but then we would go back over it later. So their foreshadowing isn't all that effective. Unless when we get to that, you go, oh yeah, I remember that I remember that from 3 months ago. My experience is nobody remembers it from 3 months ago. You do if we're constantly reviewing. But if we're not constantly reviewing, then it kind of goes, again, 5 to 7 things in, hopefully not 5 to 7 things out. So that's what the arrows mean. What other questions? These aren't the real kind of resonance structures I start with. What I'm going to start with in terms of resonance structures are things like from general chemistry. So here's a question that I will start with. And that is that I have the molecule, the OCN minus 1 ion. Okay? So overall, this has a -1 charge. So here's what I would like you to do. Give you about whatever my timer is, if I can find my 5-minute timer. There's a 15-minute timer, that's a little long. 10. Yeah, but then I have to sit here and I have to watch it, right? And then I have to turn it over. So, well, what I technically should do is not sit here and watch you. I should walk around. And this is what they tell me at the workshops I go to. Don't just sit and watch people. Get up and walk around and see if they have any questions. So these are the same people that said humor is not appropriate because it makes you forget stuff. Yeah. So I think we'll abide with the walking around. So here's my question. My question is, I'd like you to draw a Lewis dot structure, a valid Lewis dot structure for an OCN minus. Now there's going to be more than one valid Lewis dot structure, so if you get a first one done, write a second. But what I'd like you to do is to write 1 and assign the formal charges then to the atoms. And overall, those formal charges must equal -1. Okay? And in terms of your periodic table, how many valence electrons for a neutral oxygen? 6. For carbon? 4. And for nitrogen? 5. So oxygen 6, carbon 4, nitrogen 5. And there is more than one, so I want you to write 1, and then if you can write a second one, that's great. If not, I'm gonna ask you for all the possible ones that you're writing. everybody knows how to start? If you have, so there'd be 3 legitimate resonance structures for this, and if you get all 3 of them, well, and you'll know you're incorrect if your formal charges don't add up to -1. But if you have more than 1, everything has to have an octet, so that middle carbon needs to start sharing electrons to form an octet. Let's make sure you don't lose electrons along the way. If you have all 3, the next step would be to rank them from most to least stable. So, looks like people, for the most part, got at least 1. So let's start with, I'm going to have oxygen bonded to the carbon, bonded to the nitrogen. There are 3 of these. And you might say, how did you know there are 3 of them? Because I know there's 3 of them because we trial and error. Which means I will tell you how many there should be for each problem. I'll usually say there are 3, there are 2. If you're ranking, I'll sometimes say, or when you're writing the resonance hybrid, I'll say write the hybrid of the most stable 2 of 3. Because sometimes if you get 3, they average it. They're not all major contributors. Okay, so give me a structure here. Okay, for the oxygen, how many lone pairs? 3 lone pairs. Bond between O and C. Okay, how many lone pairs on the carbon? Bond between carbon and nitrogen. Triple bond, how many lone pairs on the nitrogen? Just one charges.
Oxygen will have a -1, carbon will have a 0, and nitrogen.
Okay. So just oxygen with a -1 charge. Anything glaringly wrong with that? Usually if people make a mistake, what they're going to make a mistake on is wrong formal charge. Well, first mistake, breaking the octet rule, either under or over, getting the wrong formal charge, and then when they add up the formal charges, they don't add up to -1. So that's kind of your checklist. All octets, formal charges are correct, formal charges add up to the correct number. Usually if you get those three right, it's a legitimate structure, which means if you get them wrong, if one of those things, then the structure is completely wrong. Okay, second one that somebody got. Let's go through it systematically. How many lone pairs on the oxygen? 1. Oxygen carbon bond. Lone pairs on carbon. And how many over here? 3 lone pairs. Formal charges?
Oxygen has +1, carbon has 0, and has -2.
Okay. All right. Does that one look good? Okay, third one.
Oxygen has 2 molecules. A double bond between oxygen and another double bond, and then 2 molecules.
Charges?
Oxygen 0, carbon 0, and nitrogen -1.
Okay. Anybody have any others? Okay, here are our 3 resonance structures, A, B, and C. All right, now, what is, well, first of all, these are 3 resonance structures. What is the true structure of this? The resonance hybrid, the mixture. Now, before I do the resonance hybrid, I need to know about the relative stabilities of these 3 structures, because each one feeds into the resonance hybrid as its weighted average. So in other words, the resonance hybrid is a weighted average of these 3 structures. And the idea of a weighted average is, I mean, take a look at the grades for this class, right? What are they mostly dependent on? Exams. And so they have the highest percentage that feed into them. Right? I suppose you could try a genetics analogy here, you know, something dominant and something not as dominant, but here it's based totally on energies and totally based on the math. So the resonance structure that is most stable is going to contribute most to the hybrid, which means the hybrid is going to look mostly like the most stable of these resonance structures. Okay. So we have to rank these. Okay. So what are my rules for ranking them? Number one rule that I'm going to use to determine the stability is that I would prefer to have completed octets. Now sometimes, well, completed octets is our first rule. Generally what I will do is I will ask you to only write resonance structures that have completed octets. So they automatically have to follow rule number 1. So rule number 1B would be that we have all 0 formal charges. Okay. In this case, can that happen? No, because it's a -1 anion. So then we go to rule 2, which says I want small charges, meaning plus or minus 1 versus plus or minus 2. And I would also like a small number of charges. Which one of those dominates? That's tough. So it's kind of like both of them together. So we'd like small charges and we'd like a small number of charges. Now, in this case, that eliminates, or that makes one of these three clearly the least stable. And which one is that? That's the least stable. B. Because it's got, not only does it have 2 charges instead of 1, but it's got the large -2. So B is automatically the least stable. Okay. But as far as A and C go, they're still tied. So now we go to rule number 3. And rule number 3 says that we should align the charges according to the electronegativities. So the charges should align with the electronegativities of the atoms. What does that mean?
The most electronegative charge, the extra negative charge.
So if I have the choice of putting a -1 charge on this atom, or putting the -1 charge on this atom, the -1 charge should go to the atom that's most electronegative. What happens if they have the same electronegativity? Probably those two structures have the same energy. Okay. So that's rule number 3. After that, if I can't break the tie, they're tied. Okay. So let me ask the question then of A and C then. Which of those two is the most stable? So which one is the most stable? A or C? So if you answer B or D, wrong. Okay. I got 26 number 1s, which is A. I have a B. And I have 4 C's. So what's more electronegative, oxygen or nitrogen? Oxygen is. Because remember, on the periodic table, when we go CnOF, and then we go down here, nitrogen is phosphorus, sulfur, and then chlorine underneath that. The electronegativities always work towards fluorine. So oxygen's more electronegative than nitrogen. And so therefore, A is most stable, B is least stable, and C is the second most or least, whichever one you want to say. Now what this means is that I can't know an exact sort of energy here to rank these unless I use a computer. So in this case, because B is pretty egregious in terms of having 2 charges, the resonance hybrid is not going to look much like B at all. It's going to look more like a combination of A and C with more A than C. But what does that mean? Well, let's go ahead and write the resonance hybrid then. So let's write the resonance hybrid up here with this O, C, and N. So how do I write the resonance hybrid? Number one, I'm going to average bonds and charges. That's number one and number two. So how am I going to average the charges? Well, let's just take into account A and C for this. So I'm just going to average A and C since they're going to contribute the most. So if I look at the oxygen, what is it in one case? -1. What is it in the other? 0. What's the average? Well, you might say -0.5, but I don't care about the exact number here because I don't know how much more stable A is than C. They're not 50-50. So what I would say is it's somewhere between 0 and -1. So there is some or a partial negative charge, and in chemistry we use delta to indicate partial. So there's a partial negative charge on the oxygen. That means it's somewhere between 0 and -1. Exactly what is it? Don't care. I just know it's between 0 and -1. How about carbon? Carbon is 0 and 0, so it's 0. What if it turned out to be +1 +1? Then it would be +1. How about the nitrogen? 0 and -1, so the nitrogen should be delta minus. Okay. Who has the greater delta minus charge?
Oxygen.
We agree? The greatest delta minus charge is with the oxygen. Why? Because number one, A was more stable, the resonance structure A was more stable, but because oxygen is more electronegative. So there's going to be more delta negative charge on the oxygen than the nitrogen. Okay, let's average bonds. See, I don't do anything with lone pairs. I don't average lone pairs. It's just bonds and charges. You might say, well, the lone pairs are important, right? Absolutely, because the lone pairs give you the charges. So oxygen is single, and in C it's a double. So that means it's somewhere between a single and a double bond. So we put a bond with dots. Nitrogen is somewhere between a double and a triple. So double bond, partial triple bond. What's the reality in that? The reality in that is that if I actually had that ion in real life, it's going to be the hybrid. The carbon-oxygen bond is going to be somewhere between a single bond and a double bond in terms of its length. The CN bond is going to be somewhere between a double bond and a triple bond in length. And the two oxygen and nitrogens are going to add up to -1 charge overall, but oxygen is going to have more than the nitrogen does. Okay. Short of me determining the structure of this ion, I could do this on the computer, and the computer would tell me approximately how much negative charge is on there, but we don't care. We just care about oxygen and nitrogen have some negative charge, oxygen has more. Okay. So that's how we would do this. Okay. All right. So on Wednesday, what I'd like you to do, and I worked ahead this weekend, so I did put the video, there's a video in the folder for chapter 2. I will give you some take home or some practice graded problems on Wednesday over both the hybridization and the Lewis dot structures, but I'd like you to do the readings for Wednesday. And again, if you have any questions about any of these, post them on Piazza. Even if